We can also use the integral to evaluate something called net change. So let's start on to that. So we previously looked at how the integral is related to the area under a graph, but it can also be used to complete what's called net, which means total change. So here's the definition of that. The net change in a function s of t, so a position function usually, over a time interval, usually t1 to t2, is given by, it's the integral from time 1 to time 2, of the derivative of the position function. And the derivative of a position function is a rate of change function. We would know that as, if it was a position function, as a velocity function. And that's equal to the function being evaluated at t2, take away the function evaluated at 1, t1. And since we know the velocity of the object is related to the position of the object through derivatives, namely the first derivative of the position function is the velocity function, the antiderivative of the velocity function with respect to t calculates the net change in position, which is also known as displacement. The total displacement. This isn't the same as the distance. The displacement is if I walked 1 block west, 2 blocks east, 3 blocks west, and then another block west, I would be west even though I've walked west and east. It's where I am relative to where I started. Whereas the total distance that I've traveled includes walking west and walking east and then walking west again. So it's a sum function of all of those things. This isn't calculating that. This is calculating how far away from the original starting place am I. So putting these things together, if you have this velocity function with respect to t and you integrate it from t equals 1 to t equals 2, that's the same as the first derivative being evaluated and the difference of both of those using integration rules. And as I said, the distance traveled is not the same as this displacement function or calculation, but you can actually calculate the total distance traveled. You just have to use a slightly different formula, namely from time 1 to time 2, but let's keep everything positive. And the way of doing that is to use the absolute value. So let's take a look at a couple examples of this. Hopefully it'll put things together a bit for you. So our example is a particle has a velocity, and it's measured in meters per second, of v of t is equal to t cubed minus 7t squared plus 12t. And we're going to do two things. First of all, we're going to find the displacement on 0, 4, and then we'll look at the total distance traveled in part B. So the displacement is the integral evaluated from 0 to 4 of vt dt, and so that's the same as t cubed minus 7t squared plus 12t dt, and so I get t to the 4th over 4 minus 7t cubed over 3 plus 12t squared over 2 all gets evaluated at 0 and 4, and if you do that evaluation you get 10.6 repeating. If you go and now do part B, which is find the total distance, on that same interval, we now get something interesting happening. when we take our integral from 0 to 4 of Vt absolute valued dt, there's times when the velocity function was positive and when it was negative, and the absolute value is going to make it always positive. We don't have any way of integrating absolute values, so what we have to do instead is break it into the parts that were positive and that were negative. So if you go ahead and graph this, so go grab your graphing calculator, graph your original v of t function, and see if you can see when is it positive and when is it negative. So pause the video and go ahead and do that. You should see a graph that looks something like this, and you'll notice that there's a negative area from 3 to 4, and that means that with our displacement function, that was thinking about it as a negative area. It was subtracting it away. But actually, with the total distance traveled, that's just moving in the opposite direction, which is moving. So we want to include that as part of the distance traveled. And so what we do is we break this integral from 0 to 3. We don't have a problem. So it's t cubed minus 7t squared plus 12t is getting integrated dt, but we know that the next function gave us negative area or negative distance, so to combat that I'm going to subtract that away from 3 to 4, and that'll actually add in negative area. So it's the same function, I just trick the calculation, as it were, into giving me additional positive value. So I take my function, I evaluate it from 0 to 3 using the above method. So t to the 4th over 4 minus 7t cubed over 3 plus 12t squared over 2. I evaluate it from 0 to 3 using that. Then I also evaluate it, same function, t to the 4th over 4 minus 7t cubed over 3 plus 12t squared over 2. And now I evaluate this from 3 to 4, and I subtract away the answers. By doing that, you'll find that the answer is a much higher value than 10.6, because you're also including the distance that got cancelled out with the displacement is actually being added to the total distance traveled with this method. And I calculated that this is a total of 11.83 repeating when you look at the total distance traveled, and that makes sense. The amount of extra space that was negative isn't very high. We add that space in twice, once for when we took it away before and once for adding it in. That's essentially what this calculation does. You end up with 11.83. Hopefully this gives you some basic idea on net change, and it does tie into some of the other things that we've seen, obviously, with integration. And come to class ready to try some questions.